Imagine if one day AI could learn and improve completely autonomously, without any human guidance. What would that look like? The research we're introducing today might let us see this possibility. A research team from Tsinghua University and the Beijing Institute for General Artificial Intelligence proposed a new method called the Absolute Zero Reasoner. This new approach can autonomously improve reasoning capabilities without any human-provided data. Before introducing this breakthrough, let's first look at the challenges currently faced by AI learning. Currently, large language models primarily rely on reinforcement learning to improve reasoning capabilities. Although this method does not require manual annotation of specific reasoning steps, it still depends on a large amount of human-collected questions and answers. This brings two problems. First, high-quality human data is becoming increasingly difficult to obtain. Second, if AI truly surpasses human intelligence in the future, the tasks provided by humans may not be able to meet AI's learning needs. How does the Absolute Zero Reasoning model solve these problems? Let's understand through a concrete example. Imagine you are learning programming. The traditional learning method is the teacher assigns you homework, and the teacher corrects it after you complete it. But the Absolute Zero Reasoning model adopts a completely different approach. It is both the student and the teacher. Specifically, when the model is solving a programming problem, it simultaneously plays two roles. As the teacher, it generates a programming task, such as writing a function to calculate the Fibonacci sequence. As the student, it needs to solve this task. This process is like self-play in chess, improving its ability by continuously posing and solving problems. But here's a key question. How to determine if the answer is correct? The model uses a special judge, the code executor. This executor is like a strict examiner, capable of running code and verifying if the results are correct. For example, for the Fibonacci sequence problem, the executor checks whether the function can correctly calculate the first 10 Fibonacci numbers. More interestingly, the model not only generates simple tasks, but also designs tasks suitable for its current ability level. This is like a student being able to choose exercises that match their level. For example, when the model masters basic recursion, it might generate a problem that requires the use of both recursion and dynamic programming to challenge itself. This way, it continuously improves its learning. In this process, the model learns three different modes of reasoning: deduction, induction, and abduction. Deductive reasoning is like going from the general to the specific, for example, deriving the solution to a specific problem from a mathematical theorem. Inductive reasoning, on the other hand, goes from the specific to the general, such as summarizing patterns from multiple specific examples. Abductive reasoning involves inferring causes from results, for example, deducing possible issues from the erroneous outcome of code. This multimodal reasoning ability enables the model to understand and solve problems more comprehensively. During the experiment, the researchers observed some interesting phenomena. For example, when the model was generating code, it would record its thought process in the comments. These comments were like learning notes, helping the model understand its own reasoning process. Interestingly, when the researchers removed these comments, the model's performance actually declined. This shows that these seemingly simple comments were actually helping the model learn and understand. Another interesting finding is about the use of global variables. In programming, global variables may leak answer information. For example, if in a function that calculates the maximum value, a global variable already stores the correct answer, this might make the task too easy. But experiments found that even with such leaks, the model still needs to perform non-trivial reasoning to arrive at the correct answer. This is like a student who, even knowing the answer, still needs to understand the problem-solving process. Researchers found that this behavior of pretending not to see the answer actually helps the model perform deeper reasoning, which is similar to the rationalization process in human learning. In terms of reward design, researchers experimented with various combinations. They found that simply adding external rewards, such as code execution results, and internal rewards, such as code complexity, together was more stable than multiplication or other complex combination methods. This finding may seem simple, but it actually has a significant impact on model training effectiveness. How effective is this model? It has achieved good results in programming and mathematical reasoning tasks. Even without any human-generated data, its performance surpasses models trained with tens of thousands of human-annotated examples. More importantly, this method can be applied to models of different scales and has strong generalizability. Of course, this research also faces some challenges. For example, how to ensure that the tasks proposed by the model are both challenging and not too difficult. How to balance the learning of different reasoning modes. These are problems that need to be solved in the future. Overall, the absolute zero reasoning model demonstrates the possibility of AI autonomous learning for us. It does not require manual data and can evolve on its own. This capability is of great significance for the future development of AI. Although this method is still in the research stage at present, it opens a new door for us, allowing us to see the future of AI autonomous learning.